know, you know.
Hey guys, Professor Phil Pinzoni here. I'm in Chestnut Ridge County Park, and I feel like this is a really good place to start to kind of segue in from last lecture. We talked about trophic dynamics, and especially on the East Coast. And you're going to hear a lot of people because this is actually a really popular park, but it still is really cool, this urban mixed deciduous forest. And like the name suggests, Chestnut County Park, it used to be filled with chestnut trees. Now in 1904, this parasitic fungus came in from Japan, known as Cryphonectria parasitica. The first time we actually saw it was actually in the Bronx Zoo back in the early 1900s, and this parasite quickly spread to all of the American chestnut trees, most of them. And there's only a few isolated populations where they're not dead. So this area was totally dominated by chestnut trees. Now you're looking at hemlock trees, which leads us into today's lecture. We're talking about single cohort stand development. So after these American chestnuts had died with this parasite, we had these hemlocks in this area take over. So you can see that they're generally the same size, so this is considered a single cohort. Now, in terms of trophic dynamics, to segue in from last lecture, think about chestnuts. Think about the actual nut of a chestnut. They're rather large, they're packed full of calories, and in the Appalachian region, 1 out of every 4 trees was an American chestnut tree. So think about all of that energy coming into these ecosystems, feeding small mammals, which were then feeding more and more predators. So you get this trophic cascade, right? This bottom in control from the American chestnut. In modern times, the chestnut has died and it's been replaced. So that is an example of bottom out control.
So a quick overview of today's lecture. I'm going to introduce these single cohort stands. Then we'll get into the 4 developmental stages, and I'll look through Chestnut Ridge looking for specific examples of the stand initiation stage, stem exclusion stage, the understory reinitiation stage, and then finally old growth stage. And I'll look and describe the patterns and examples that I encounter.
So I just want to reiterate something. I'm giving you examples of specific stands. Now, if we zoom out into this larger forest area, you'll notice that the actual forest is made up of individual different stands. Those stands are driven by a whole slew of different abiotic and biotic factors. So we saw the hemlock stand, we saw the red pine stand, they have a specific microsite. They have specific pH in their soil. They have specific organisms that they interact with, allowing those stands to be established there in the first place and then reestablished later. Now, each of these stands in their different microsites are going to have different disturbances, which is going to allow the progression of those specific stands. I just wanted to relay that information that this entire forest system that I'm hiking through today is made up of all these different stands that have their own attributes that are interacting with their surrounding abiotic and biotic factors. Although this is a multi-cohort stand, I'm going to take the time to describe this idea of after a disturbance, you get different species that are that infiltrate that area. Obviously, we talked about disturbance, and depending on how severe disturbance, you're going to get these different assemblages occurring. Now, here we have this stand dominated by black cherry, oak, we have some hickory, and we have maple. Now I'm going to use this stand specifically and talk about these two theories that we call successional theories. So again, succession is the idea that certain species actually succeed other species depending on forest age. So the first of these two theories that help describe these forest patterns are relay floristics. So in relay floristics, kind of like a relay race, you have certain species that enter that area and then they die, and then other species fill their niche, they die, and then other species come in. So similar to like a relay race. Here you have these first successional species, and in a different patch I witnessed a lot of cottonwoods, and I knew that that stand was going to be more recently disturbed because we know that cottonwoods, they have wind dispersed seeds and they could only germinate in full sunlight. Here we have an older stand that has more shade resistant species just getting their start. So right behind me here is this American beech. We know that American beech is more shade tolerant. There are red maples in the background as well, and they're the kind of smallest trees in this area. So it's a good description of this succession. It's a good description of relay floristics because we have these more sun tolerant species that are more established that are now and now we're seeing this succession of more shade tolerant species. Eventually, if this is not disturbed, you'll have dominant shade tolerant species with some emergent trees that might be sun tolerant, but we're going to have this area being more dominated by shade tolerant species. So we have relay floristics, and the second theory is initial floristics. Initial floristics postulates that species in an area actually establish kind of at the same time. So after a disturbance, you get a bunch of species that become established, and certain species have a ecology that is, live fast, die hard. They have a short lifespan. They carry out their reproductive effort, and they complete their life cycle in a short duration, while there are some more there's some trees that live a longer life that takes longer for them to reach maturity and reproduce. And the succession that we see is just that aspect. Those species that you see have got their start at the same time. It's just that biology interaction. It's just the idea that certain species live longer. They have a different life history. Relay floristics is usually supported by a lot of papers. However, in some publications, the initial floristics theory is actually supported. So again, the complexities of ecology that we're learning about. It's really site specific for the patterns that you're going to see, depending on what you're looking at, depending on the species, the area, the topography. Either or of these hypotheses are going to help describe those patterns. So here we are in a stand of red pines. You can take note that most of these trees are exactly the same. They have the same DBH, right? They have the same diameter at breast height, which is another term that we're going to talk about now. This is a single cohort. So this is more specifically a single species, single cohort. And we also talk about a community like this. If all the trees are generally from the same cohort, we call them even-aged cohorts. So these red pines, you'll notice, are evenly spaced. So this has been artificially planted by some foresters in the area. Again, just so you know, this is not how even cohorts in natural systems look. This has been planted here. Now, depending on how the established trees are spaced, these trees are going to grow differently. So trees that have a larger gap separating them from other members of their cohort, they're going to grow taller, they're going to grow more robustly if they have the similar soil properties. Trees that are closer together are going to grow less robustly. They're going to grow slower. So again, here's a great example of an even-aged single species cohort to better understand how cohorts establish themselves in ecosystems in our own backyard. So there are going to be 4 stages that a single cohort is going to go through. Now, depending on the ecosystem, this can change. They don't have to go through all of these stages, but generally speaking, there are 4 stages. Number 1, we have stand initiation. Then we have stem exclusion. Then we have understory reinitiation. And finally, these stands turn into an old growth habitat. So to talk about stand initiation, that is exactly what it sounds like. These trees getting started in an ecosystem. We talked about the chestnut blight, this fungus that killed chestnuts that used to live here. Chestnuts used to dominate this very area. This has been replanted by red pine, in an unnatural way, right? Because you can see the structure of this specific stand is obviously not how nature works. These plants aren't evenly spaced like this. But you have individuals, juveniles, for example, when they're spaced this far apart from each other, they have this free growth. They grow really horizontal, and they they have a ton of space to occupy, and they take in a lot of sunlight. There's ample soil resources, so that's great, right? I mean, you get in this situation, because it's been planted by humans, they had wide gaps between individuals, which allowed this stand to grow rapidly in a very short period of time.
In terms of disturbance, you're going to have the stand initiation occur differently depending on how severe those disturbances are. So for a light disturbance, the trees just on the perimeter of that disturbance are going to release seeds, and tree recruitment is going to occur, and those trees are just going to advance in that lightly disturbed area. In a more severe disturbance, a medium severity disturbance, you're going to have stand initiation mainly by buried seeds and sprouting from stumps and roots that remain as biological legacies. In high severity disturbances, Seed dispersal is going to be the primary way that trees establish themselves again, because after a really intense and severe disturbance, the soil is bare and there are very few biological legacies left. Sometimes after specific disturbances, all this litter has accumulated on the forest floor, branches and stems and all these different plant materials. And when you see a system like this, recruitment and stand initiation does not readily occur. It's very difficult for seeds to become established in a habitat like that. This is why when loggers clear an area, they pile all their debris up into these piles and then they burn them. So this method is called slash and burn to allow this stand initiation to occur unimpeded.
So we've talked a lot about the spatial aspect of ecology, how certain areas of the forest receive more sunlight, how certain areas have more water available to them. Depending on the aspect of slopes, we learn about this sense of spatial interactions. But we haven't really talked a lot about this temporal aspect. So right behind me is this giant, absolutely massive red oak. And we hiked past some juvenile red maples, and they put out their seeds in a different fashion. So this red oak behind me, it puts out acorns in September. Those acorns do not germinate until the following June, so they actually have to be overwintered for them to germinate. Now, in June, red maples, they release their seeds, and their seeds can germinate right away. So they actually germinate at the same exact time. When we take into consideration disturbances, we can have totally different patterns for establishment. For example, if we have a May disturbance, let's say a brush fire, all those acorns released in September are going to die, and the maples that year are going to release their seeds at June after the disturbance. They're going to get their start that following year in September. The red acorns are going to be dropped, and then in June, those red acorns are going to germinate. So already with a May disturbance, you're going to have red maples. They're going to be a full year ahead of them.
If the disturbance occurs in October of year one, then it would kill all the red oak acorns, and red maples would start growing there in year two following their seed dispersal in June. However, the red oaks would not start growing until year three following dispersal of acorns in the September of year two and that overwintering period. Now, if there was a disturbance in June, July, or August of year one, then it would kill the red maple seedlings growing from seeds, but it would not kill red oak acorns as they disperse in September. Thus, this would result in both species becoming established in the site in year two, giving neither of them the initial floristic competitive edge. So I really like this idea of plant timing or plant phenology that actually drives the stand initiation of these two species that co-occur in our own backyard.
The next stage, we have stem exclusion, which is a fancy word for tree death. In the second stage, after long enough time, you're going to have individuals that are possibly too close to their neighbors, and they're going to not access enough sunlight for one, not access enough soil nutrients, and they're actually going to be excluded. They're going to die, right? In this system that we're looking at now, again, it's artificial because foresters specifically planted these individuals far enough apart so there wouldn't be much stem exclusion. So in the stem exclusion phase, these individual trees, they're going to have more of a plastic growth. Their canopy is going to shift in structure given the available light. Not only is the canopy eventually going to close and individuals are going to die and be excluded, think about canopy closure as well as root closure. The roots can only grow and access so many water and nutrient pools. So when we get to this high dense forest, not a lot of light's coming in, and there's only so much nutrients and water available. So individuals are going to be excluded.
So unlike the man-made single species stand I found in Chestnut Ridge, a single species stand that occurs naturally is going to have the following attributes. They're going to have irregular spacing for two reasons. First, because simply by chance. Some locations are just going to receive more seeds just by chance. Secondly, there is the micro environment. So some areas are going to be more favorable, like having higher soil fertility. Areas with higher soil fertility are going to experience greater seed germination and seed establishment. So trees, when they are grown with more room in between them, they're going to have wider canopies than those with less room. By growing wider, they will get more space for photosynthesis, and thus they will be healthier and less likely to be excluded when they are older. So if you look at the right, this blue region are trees that are widely spaced, and you could follow their age, youngest to oldest. No stems actually become excluded in the old stand. Enough space is there for them to access light and nutrients and water, so no stems are excluded. Now the red zones show individuals that are more closely spaced, and you do actually see stem exclusion as time progresses. Now, while the height of all trees is going to be initially the same because they're the same species growing in a relatively very similar habitat, the trees that have wider spacings are eventually going to grow taller than the trees that are closely spaced. So stem exclusion will occur most often for trees that are most closely spaced, because that will result in them becoming shaded by trees that had more space and were also faster growing. The closely spaced shaded trees will have lower net photosynthesis, will grow more slowly, and thus more likely to be excluded.
So this part of the forest here is not only a good example of a multi-species stand, not a single species stand, but also a good example of a multi-cohort stand. You'll notice this cherry right here, this oak to the left, are generally similarly aged. However, there is this smaller beech over here and an even smaller beech right here. So we have, in this little vicinity just right before us, we have three, and not to mention this really small beech right there, we have 4 different cohorts living in this one area. So totally different. We're going to focus more on this next lecture, but I just saw this and thought this was a really good example of a multi-species, multi-cohort stand.
So let's take a closer look at a mixed species stand, again in a single cohort. So in a mixed species stand, you're going to have this canopy differentiation because these different species, they're going to grow at different rates. So the subcanopy is going to be made up of saplings that are 1 to 5 inches at DBH. Now, they're not younger, right? This is single cohort. So after a disturbance, all these trees emerge, around 10 years of each other. So they are a single cohort. So these subcanopy trees, they're not going to be that much younger, if at all, right? They're just going to be slower growing, more shade tolerant species. And they're definitely going to have to be shade tolerant because otherwise they just wouldn't be able to live in these conditions. Now the canopy consists of pole-sized trees that are 5 to 15 inches at DBH. Some of them are even larger. Some will be sun-loving species and others will be shade-tolerant species. The top of their crowns are going to be exposed to the sun, but the sides of their crowns have side shade from adjacent trees. Onto the emergent trees, these are going to have their crowns above the canopy trees. This occurs because either they are faster growing species or because they started growing on better microsites. These are going to be sun-loving, shade-intolerant species because their crowns are fully exposed to the sun. Let's take a look at this northeastern example. Focusing on stands of red oak, red maple, and black birch, these researchers carried out a study that helped us better understand these mixed single cohort stands. So if you guys remember earlier in the lecture, I was talking about how oaks and maples, their timing of life history events is different, as oaks drop their acorns in September and those acorns must overwinter and then germinate in June. So we learned that disturbances along this calendar year can drastically change the establishment of those two species. For simplicity's sake, we're going to just pretend that these red oaks, red maples, and black birch in this specific study all germinated at the same time. So they become established in a single cohort with similar heights for the first 15 years. After 15 years, however, at which point the canopy was most likely closed, the red oak actually begin to grow fastest and form the canopy, while red maple and black birch grew slower and became the sub-canopy. Remember, these are still trees that are the same age. Now, this differentiation in growth rate was likely due to different shade tolerance following canopy closure, with red oak being the most sun tolerant and red maple the most sun intolerant or shade tolerant. These differences in growth rate continue. When the forest is 60 years old, red oak forms the canopy and black birch and red maple form the subcanopy despite being the same age. The stem exclusion stage is not really shown here because only living trees were tested in this specific study. This temporal pattern of tree growth was reconstructed from real mature trees by cutting each tree trunk at 1 meter intervals. So you can see this picture in the bottom left, 1 meter intervals. These trees were cut and you could count and utilize those rings at each height. This reconstruction made it look like the forest was very open when young, but that is just an artifact of only a few of the many trees that were alive during the establishment stage being able to survive stem exclusion and becoming mature trees. So although this reconstruction made it look like this forest was very open when young, just not a lot of trees at all actually made it from the initial initiation all the way to this later mature stage. A term associated with stem exclusion that you should be familiar with is the -3/2 thinning law. So while stem exclusion occurs primarily during the stem exclusion stage, it is actually a continuous process that begins during the stand initiation stage and continues through the old growth stage. So looking at this specific example, this beech forest was monitored for 120 years. Now, a general law has been found that relates the size of trees with the number of trees in a stand. So basically, if you plot the log transform number of trees on the x-axis, and again, the log of 10 is 1, the log of 100 is 2, the log of 1,000 is 3. So if you plot the log transformed numbers of trees on the x-axis and the log transformed average weight of individual trees on the y-axis, the slope is typically -3/2. So the slope is negative because it ascends from the bottom right of the graph to the top left of the graph. A positive slope ascends from the bottom left to the top right. So this is a negative trend. So this slope is followed as a stand ages, indicating that as the average number of trees decreases due to stem exclusion, the average size of surviving tree increases. This change has a predictable slope that allows predictions to be made about the number of and size of trees that will occur at different numbers of years in the future. So really interesting rule that these researchers realized, this -3/2 thinning law, a law that foresters know all too well.
Given long enough time, eventually you'll get this understory reinitiation.
Like I was just mentioning, the understory reinitiation phase is when there is an increase in understory plants. More light penetrates the forest floor that is created from these more opened little micro habitats. Sometimes soil space opens up as the organic litter added by the canopy provides nutrients and holds moisture for small shade-tolerant seedlings and saplings. Those shade-tolerant seedlings and saplings are thus experiencing commensalism, a positive outcome for them, and a neutral outcome for the canopy trees that provide them with organic matter. So this is going to be an example of relay floristics as well. You're going to have this almost relay race in a specific location of different species succeeding each other. Now, these openings are not truly going to be from a disturbance because a disturbance involves many trees dying at once. So we normally don't call a small scale disturbance like an infestation or a fungal parasite for one individual a disturbance, but you're going to have, different fungi and different herbivores and parasites creating this or catalyzing this understory reinitiation phase as one mature tree is felled by this disturbance, which again, really small scale disturbance will allow this opened niche space for something else to come in. This understory reinitiation phase, for two reasons, does not create multi-cohort stands. Firstly, because these gaps are too small. While they might allow multiple seedlings to establish at one time, following the stem exclusion stage, typically only one or two of the seedlings will survive to become mature trees. Second, the gaps in which the understory reinitiation occurs are formed frequently, so every few years, and this results in continuous new establishment rather than the infrequent establishment that would have to happen to create a totally new cohort.
Although this is a multi-cohort stand, this is actually a really good example of the third stage, that understory reinitiation stage. As you can see around here, there's a lot of downed trees. There's a lot of logs that are decomposing, and as they fell, more light was available to this specific location, and there was more soil nutrients available. As you can see now, we have these larger cohorts still looking pretty healthy. The oldest of them have now died, and we have this new initiation, this reinitiation of these younger American beech trees. So although it is a multi-cohort stand, it's a really good example of that third stage, that re-establishment stage. Finally, you get into old growth ecosystems. Now these are the rarest of ecosystems, right? They're not prevalent in today's world. Old growth, we looked at all those characteristics that old growth forests have.
Those structural features include trees of many different sizes and ages, including small young trees established during understory reinitiation, and as well as many logs in different stages of decay from recent and long ago stem exclusion. Old growth forms as individuals from initial single cohort die due to the competition that creates stem exclusion, in addition to disease and old age. Now, a transitional old growth occurs when the understory trees grow upward and fill the gaps that formed when trees from the initial cohort died due to stem exclusion. Now, the term true old growth occurs later when no trees remain from the original cohort. This thus occurs following many years of transitional old growth. Stem exclusion continues during the stages of transitional and true old growth. Now, the idea of a climax forest differs from that of old growth. The theoretical climax forest has a canopy of trees of shade tolerance that are long-lived species under which individuals of the same species become established as seedlings and then grow until they enter the canopy by filling a gap. In contrast, the old growth idea does not limit what type of species will dominate in the stand, nor which species will fill in the gaps. Age at which true old growth forms is related to maximum age of species. Again, we know this. So a black willow has a maximum age of 100 years. A American beech has a maximum age of 400 years, and a sequoia has a maximum age of 3,000 years. Thus, you can't have a true old growth in a stand of black willow unless it's at least 100 years after the disturbance that initiated their stand, or 400 years later in a stand of beech, and at least 3,000 years of in a stand of sequoia, right? So remember that this terminology, this old growth terminology, is highly dependent on the species that grow there. Now, the next patterns I'm going to discuss, I absolutely love talking and teaching about, because these old growth patterns, they actually transcend just tree biology and are applicable to many other life forms. So species of the oldest trees on the planet are not ever found in closed forest stands. Instead, they grow in open forests with harsh environments. So this is the pattern I want to bring up. Across the entire planet, the oldest living organisms never are living in a suitable, hospitable habitat. Almost always, individuals that live extremely long lives live in these incredibly demanding environments. So the oldest trees in the entire world are bristlecone pines found in California. The oldest individual bristlecone pine is greater than 5,000 years old. It's actually 5,070 years old based on tree ring dating. On the East Coast, it's actually in our own backyard. In the Niagara Escarpment, we have these really long-lived white cedars that are just over 1,200 years old. Trees of some species are able to survive to be so old for 5 reasons. Number 1, they have abundant chemicals packed in their tissues, including their phloem. So the phloem, again, transports photosynthate, and it's found between the bark and the xylem. So this reduces the palatability to insects whose adults or larvae try and extract nutrients from their phloem. The second reason is that their xylem contains abundant resin ducts through which resin flows. This sticky resin reduces palatability of the xylem insects as well as bacteria and different fungi. The third reason is that this is a really harsh environment. So competition is going to be very low. Pristine environments are extremely competitive places, but these harsh environments, these individuals are not going to be reduced through competition. In a harsh environment, additionally, they're going to grow more slowly. This slow growth reduces cellular activity, which also reduces the wear and tear on their bodies, allowing them to live longer. And finally, since individual trees are so isolated in their harsh environments, they are likely to have diseases spread to them from neighboring trees of the same species. I absolutely love these final ideas of this lecture. Thank you for your attention. This was single cohort stand development. The next lecture, we're going to be looking at multi-cohort stand development. I hope you guys enjoyed my hike and this video. Remember to stay safe and stay happy and healthy, and I will get back to you later this week. Definitely start studying for exam number 4, and I will be posting an extra credit activity shortly, hopefully by Friday. All right. Thank you guys. Enjoy your night. Bye.
No, you know.